Welcome to this comprehensive guide on implementing steering behaviors in Unity 3D, tailored for beginners in game development. We'll explore how these fundamental AI concepts can bring your game characters to life, making their movements dynamic and intelligent. This tutorial will cover the core principles and practical application of seek, flee, and wander behaviors, providing a solid foundation for more advanced AI. Steering behaviors enable autonomous objects to move realistically within a simulated environment, using local vectors and forces. These behaviors are crucial for creating believable AI agents that can react to their surroundings without direct player input. They form the backbone of many AI systems in games, from simple enemy movements to complex crowd simulations. These behaviors determine how an AI agent navigates its world, with primary examples including seek, flee, and wander. Each behavior serves a distinct purpose, allowing agents to pursue targets, escape threats, or explore their environment naturally. Understanding these three core behaviors is essential for any aspiring game developer. Seek behavior steers an agent directly toward a specified target position, calculating the most efficient path. This is a foundational behavior, often used for AI characters that need to approach a player, collect an item, or move to a designated point. The agent continuously adjusts its direction to close the distance to its target. Implementing seek involves three essential velocity vectors: current, desired, and steering velocity. The current velocity represents the agent's immediate movement, while the desired velocity points directly towards the target. The steering velocity is the force applied to bridge the gap between the current and desired movement, guiding the agent effectively. First, calculate the desired velocity by subtracting the agent's position from the target's position, then normalize it and multiply by max speed. This ensures the desired velocity vector has a consistent magnitude, representing the maximum speed at which the agent wants to move towards its target, regardless of distance. Next, determine the steering velocity by subtracting the current velocity from the desired velocity, clamping its magnitude by max force. This clamping prevents the agent from making overly sharp or instantaneous turns, ensuring a more realistic and smooth change in direction. The max force acts as a limit on how aggressively the agent can steer. Apply this steering velocity to the agent's current velocity each frame, then update the transform position for smooth movement. This iterative process allows the agent to continuously adjust its path, gradually aligning its movement with the desired direction. The time.delta time ensures frame rate independent movement, making the behavior consistent across different hardware. For a natural look, use transform.lookat or quaternion.lookRotation to manage the agent's rotations. This ensures that the agent not only moves towards its target but also faces it, enhancing the visual realism of the behavior. Without proper rotation, the agent might slide sideways, which can look unnatural. Flee behavior is the opposite of seek, directing the agent away from a target, often by multiplying the seek force by -1. This behavior is crucial for creating AI that avoids danger, such as enemies running from a powerful player or civilians escaping a threat. It prioritizes increasing distance from a specific point. Key steps include calculating the direction from the target to the agent and applying a force in the opposite direction. This effectively pushes the agent away from the threat, creating a clear escape trajectory. The calculation ensures the agent always moves directly away from the target, maximizing its distance. Ensure the agent maintains a safe distance from the target, which can be set using the NavMesh agent's stopping distance. This prevents the agent from getting too close to the threat before initiating its flee behavior, providing a buffer zone for safety. The stopping distance parameter is a convenient way to manage this threshold. Wander behavior allows an agent to move randomly when it has no specific task, creating dynamic, unpredictable movement. This is ideal for ambient AI characters, wildlife, or enemies patrolling an area without a fixed path. It adds a layer of realism and unpredictability to the game world. One common approach involves setting a circle in front of the agent and choosing a random point on its circumference as a temporary target. The agent then steers towards this temporary point, and as it approaches, a new random point is selected, creating a continuous, seemingly aimless movement pattern. Increment the wander angle slightly each frame to ensure continuous, natural movement, applying a normalized force towards this random target. This subtle adjustment to the target point on the circle's circumference prevents jerky movements and creates a smooth, organic wandering effect. The normalized force ensures consistent speed. Another method selects a random position within a defined area, moving the agent there, and repeating the process upon arrival. This approach is simpler to implement for basic wandering and can be effective for agents that need to cover a larger, less constrained area. Once the agent reaches its destination, a new one is immediately chosen. To prevent agents from getting stuck, implement a timer to choose a new destination if the current one takes too long to reach. This is a crucial failsafe, especially in complex environments where agents might encounter obstacles or get trapped. The timer ensures the agent remains active and responsive, even if its path is blocked. Let's set up our Unity project. Start by creating a new Unity project using the Universal 3D template. This template provides a good starting point with optimized settings for 3D rendering, which is ideal for visualizing our steering behaviors. Ensure you give your project a descriptive name. Import necessary packages like AI navigation, then use Pro Builder to create your environment. The AI navigation package is essential for generating nav meshes, which our agents will use for pathfinding. Pro Builder, a powerful modeling tool integrated into Unity, allows for quick and efficient level design directly within the editor. Finally, bake the nav mesh by adding a nav mesh surface component to an empty object and adjusting parameters like radius and height. Baking the nav mesh creates a navigable surface that our AI agents can understand and traverse, avoiding obstacles. Properly setting parameters like agent radius and height ensures the nav mesh accurately reflects the agent's physical dimensions. Now, let's dive into C# scripting in Visual Studio to define these steering behaviors. We'll create individual scripts for seek, flee, and wander, attaching them to our AI agents in Unity. This modular approach allows for clear organization and easy modification of each behavior. For the seek script, we define public variables for the target, max speed, and max force, along with a private velocity vector. These public variables allow us to easily adjust the behavior's parameters directly within the Unity editor without needing to modify the code. The private velocity vector tracks the agent's current movement state. The update method calculates desired velocity, steering force, and then updates the agent's velocity and position. This method is called every frame, ensuring continuous and responsive movement. The calculations within update are the core logic that drives the seek behavior, constantly guiding the agent towards its target. The flee script uses a nav mesh agent, defining a safe distance and flee speed. Utilizing Unity's built-in nav mesh agent simplifies pathfinding for fleeing, as it automatically handles obstacle avoidance. The safe distance determines how close the agent will allow itself to get to the target before actively fleeing, while flee speed dictates its pace. In its update method, it calculates a run-to position away from the target and sets the nav mesh agent's destination. This run-to position is dynamically determined based on the target's current location, ensuring the agent always moves in the most direct path away from the threat. The nav mesh agent then handles the complex pathfinding to reach this calculated safe point. For the wander script, we define a wander radius, a timer, and also utilize a nav mesh agent. The wander radius determines the area within which the agent will choose its random destinations, while the timer controls how frequently a new destination is selected. The nav mesh agent again provides robust pathfinding capabilities for navigating the environment. The update method increments the timer, and when it reaches wander timer, a new random destination is calculated and set. This time-based approach ensures that the agent doesn't constantly change its mind, leading to smoother, more believable wandering. Once the timer elapses, the agent commits to a new random point within its wander radius. The random wander target function ensures the random point is on the nav mesh, preventing agents from getting stuck. This is a critical helper function, as simply picking a random point in space could lead to agents trying to move through walls or off cliffs. Nav meshed, sample position intelligently finds the closest valid point on the nav mesh, guaranteeing traversable paths. A helpful tip: Adjust the stopping distance in the NavMesh agent component for more natural-looking movements. A smaller stopping distance will make the agent approach its target more closely, while a larger one will cause it to stop further away. Experimenting with this value can significantly impact the perceived realism of your AI's interactions. Combine A** pathfinding with these steering behaviors for even more realistic AI navigation. A** pathfinding provides efficient global pathfinding through complex environments, while steering behaviors handle the local, nuanced movements and reactions to dynamic elements. This combination creates highly intelligent and responsive AI agents. To avoid agents moving through targets, implement an arrival behavior that slows the agent as it approaches its destination. This prevents the agent from overshooting or colliding with its target, leading to a much more polished and believable interaction. The agent smoothly decelerates, coming to a graceful stop. For truly realistic wandering, consider adding states like sleeping, eating, or curiosity to your AI agents. These additional states can be triggered based on environmental cues or internal timers, making the agent's wandering behavior more purposeful and engaging. This adds depth and personality to your AI characters. By integrating these elements, you can create compelling and educational game AI in Unity 3D. Mastering seek, flee, and wander behaviors, combined with smart project setup and scripting, will empower you to build dynamic and intelligent game worlds. These foundational skills are invaluable for any game developer. Thank you for watching this guide on steering behaviors. We hope this helps you in your game development journey. Remember to experiment with these concepts and adapt them to your specific game needs. Don't hesitate to explore further and build upon these foundational AI principles.